So the Gibraltar deposit is a fairly unique deposit in the Western Cordillera, as it is a ductily deformed copper moly system. And copper mineralization and associated alteration are intimately associated with ductile shear zones and the development of a penetrative S1 foliation. Some work that we've done recently has shown that aqua-regia-derived iron-titanium ratios can be utilized as a proxy for alteration in this deposit. So in this talk, we're just going to take a look at how we're utilizing oriented core data, 3D structural modeling, and these iron-titanium ratios to model the degree and distribution of alteration in the system. Just a bit about TerraLogic itself. We're a wholly owned subsidiary of Eagle Plains Resources out of Cranbrook, BC. We offer a full range of exploration services from boots on the ground, grassroots exploration, all the way up to resource definition and that sort of thing, all over Western Canada. And for the last 3 years, I've been running the infill and exploration drill programs at the Gibraltar mine. So the mine itself is located 40 kilometers north of Williams Lake, BC. It's hosted in the late Triassic Granite Mountain batholith. This is a zone calcalic system that intrudes Quesnel terrain rocks. And we have it bound by the Fraser Fault system to the west and the Quesnel Fault system to the east. The mine itself fired up in 1972, then shut down, and then in 2004, Taseko took it over and brought it back up into production. We're looking at about 1.6 billion short tons of ore at 0.28% copper, totaling about 3.1 billion pounds of copper in the ground as of last spring. So, okay, I got a bunch of animations here. Hopefully this works. If we can click on that, we'll see what happens. There we go. Okay, so this is a little mine tour. We're going to cruise into the Gibraltar West pit here. This was the first pit that was put into production in the 70s. Over to the plant and mill here with Gibraltar East pit in the background. And then as we cruise to the east, we're going to be taking a look at the current pits in production. Right here we have the in-pit crusher and the conveyor to the mill. This is the granite pit, and this is the Pollyanna pit. And we're just going to fly in and take a look at some of our drone imagery and look at the slope instabilities of the pit. Bumping down now to the 3,300 level, or 3,200 level, sorry. If we look at mineralization, we can click on that again, please. We're going to bring in copper with drill cores. And as we fly to the west, we're going to wrap all those intervals with a 0.15% copper grade shell. You can see we have two well-defined trends of mineralization separated by this south-dipping red structure. This is known as the Granite Creek Fault. This is a reverse fault, and basically granite mineralization has been thrust up on top of Pollyanna mineralization. As we come back around, we're going to bring in a series of D2 north-south striking strike-slip faults, which cross-cut the deposit and are important. And then finally, we'll rotate around and end up looking down mineralization in granite pit. So the host rocks themselves, we have a pretty simple series here. We have an uppermost tonalite and a structurally lower trondhjemite. These form a continuous fractionation series. They can be discerned in the field with total mafics as well as silica, and calcium over sodium ratios, or sorry, sodium over calcium ratios in the feldspars. It's pretty gradational, and it can be tough to discern these by eye once they've been deformed and altered. All of these rocks have been variably deformed, altered, and mineralized. And I won't get into the details here, but one thing that's important to note is that the host system that we're dealing with is relatively predictable and homogeneous in terms of its iron and titanium ratios. If we look at mineralization, bulk mineralization here is hosted in sheeted veins and meter-scale ductile shear zones. We have chalcopyrite, some moly, and a little bit of bornite hanging around. Gang mineralogy is your standard stuff: quartz, chlorite, muscovite, sericite, anchorite, magnetite. What's notably absent from this deposit is the lack of any mineralized hydrothermal breccias or syn mineral dikes. Excuse me. Taking a look at alteration here, we have a fairly simple alteration system. We have deuteric and propylitic alteration. We have a quartz chlorite alteration assemblage, and then finally a quartz sericite pyrite alteration assemblage. Alteration here is, manifests itself pretty much as centimeter to decimeter scale alteration envelopes around veins. And another thing that we're lacking here that you see in a lot of porphyries is the presence of any potassic alteration in terms of K-spar or biotite. Looking at some whole rock data here, these are alkali alumina plots. On the left, we're looking at the logged alteration assemblage. We see a nice trend, strong trend from unaltered rocks here down to potassic-rich mica. So what's happening here is we're adding potassium and we're losing calcium and sodium. There's another weak trend towards the origin. This has been interpreted as calcium enrichment. And then finally, we have some sodic alteration hanging out up here, which is currently being logged as silica alteration. But we'll fix that. On the right, this is classified by total sulfur. This is just basically an analog for sulfide mineralization. And we see a nice increase in total sulfur as we approach that K-mica end member. So whole rock data is great. I love it, but it is expensive, and it's also always lacking in historic data sets. So I'm always looking for ways to take that Ockerija data and use it for alteration vectoring and that sort of thing. And in this case, I really like iron and titanium. And this is because of the way that iron and titanium partition into different minerals of variable solubility as the rocks are hydrothermally altered. So if we take a look at titanium, fresh intermediate rock, well, the titanium will be resident in minerals such as ilmenite, titanite, augite. And these minerals are partially digestible in an Ockerija solution, so we will get some of that titanium out. As we break that mineralogy down and alter the rocks, we don't add or subtract any titanium, but we do change the mineral species that it's hanging out in, and we usually end up with things like rutile or anatase or brookite, which are very resistant, tough to break down via Ockerija, and we don't get a lot of that titanium out of the digestion. If we look at iron is the complete opposite. So when we look at iron in a fresh rock, the majority of it in an intermediate rocks hanging out in iron silicates. These are partially soluble in an Ockerija digest. As we break those minerals down and alter the rock, we tend to get most of our iron in highly soluble minerals such as iron carbonates and sulfides, where we can get a lot of that iron back from an Ockerija digestion. So it's that partitioning as well as the fact that we're using a partial digestion here that allows us to use this simple alteration indices and really take advantage of a lot of historic data that's available to us. This is a log XY plot for iron with Ockerija on the Y, whole rock on the X. And we see for unaltered rocks here, we have a fairly nice linear trend sitting below the 1-to-1 line. We're getting about 60% of our iron back. This is a linear trend because this is a fractionated series, and as we fractionate that rock, we drive it towards the origin. If we add our altered rocks to this, we see the majority of them plot much closer to that 1-to-1 line. And that's because we move that iron from partially soluble minerals to highly soluble minerals in the Ockerija digest. We also see quite a few altered rocks plotting up here, and that's because we're actually adding iron to the system typically when we alter it and mineralize it. Same plot, but for titanium. A little messier, but we do have an unaltered linear trend up here showing the same effect from fractionation. And if we add our altered rocks to this, we see the majority of those are all plotting well below where our unaltered rocks are plotting, and that's because we're moving that titanium into a highly insoluble mineral species. We're getting some stuff plotting down here because we're not losing titanium, but we're diluting it by the addition of silica, iron, and all those good things. So the fact that iron and titanium behave oppositely basically means that if we ratio them, we're amplifying the effects of that hydrothermal alteration in our geochemistry. So this is a log probability plot of iron over titanium. We have a nice curve here with a couple of inflection points. These inflection points coincide with changes in logged alteration assemblages from the geos that were logging them. And we can start picking out iron to titanium ratios that are going to be important when we get our 3D model and we want to start classifying the alteration type. How am I doing for time?
About 5 to 10 minutes.
Left?
Yeah, left. Yeah.
Okay. All right, so on to structure. Basically, we've had 2 deformation events here. D1 was a brittle deformation event, north-south compression. This resulted in a series of reverse ductile shears and that penetrative S1 foliation. D2 was a much younger, brittle translational event, and it resulted in those north-south structures that we saw in the animation before. And most importantly, that D2 event resulted in the localized rotation of S1 and the older mineralized system. So structure was always important here. In 2016, we fired up an oriented core program. During that time, we developed a oriented core QA/QC software package, which integrated with the Reflex IQ logger that came out that year. And it basically let us do some neat stuff. This was based on the work of Russell Myers and Chris Brown, of course, our bamboo diagrams. And it allows us to visualize that drill string and look at lock angles between runs. And that allows us in turn to establish confidence ratings for those runs. It also really lets us in real time get back to the drillers and give them feedback on how they're doing. And then finally, if we see fit, we can take some not great data and rotate it into more accurate data. Here's the results of the oriented core program. I'll just quickly, south to southwest dipping, S1 foliation, similar strike for the veins, slightly steeper dipping. But that data is pretty messy, and that's because it's been affected by D2. So we need to define some structural domains, code our structural data accordingly, and then look at stereo nets for each individual domain. And we get a nice clear picture here, southwest on this side, on the west side of connector fault. South-southeast, across another fault, we're looking at southeast oriented core, or S1, and then finally south dipping S1 in the other domains. Okay, so now we've defined our structural domains, we've coded all our structural data with which domain it is in, and then we do domain-constrained S1 modeling using the form interpolants in Leapfrog. And we'll just hit this animation as well. So there we go, we're just gonna pick this domain. This is the saddle fault, this is the gun fault. So we have a fault block in here, and as we rotate around, we will see the input data, surficial from pit mapping, as well as declustered and corrected downhole structural data. As we rotate around to the west, we can see the results of that S1 modeling sitting in there. As we zoom back out, we can take a look at the geometry of the deposit as a whole with the different S1 orientations from domain to domain. I didn't have time to shorten this one, so we're going to just rotate into a plan map here as well to look at it that way. So there we go. So now we've built our domain-constrained structural framework, and it's basically time just to plug in our iron to titanium ratios and have a look at them. This is iron over titanium for these holes. As we bring in our structural trends from Leapfrog, we can see how these structural trends are going to help interpolate the alteration as we model it. And here's the resultant model from this particular section. Orange and yellow is basically I just call it highly altered rock. And then if we bring in the mineralization, there we go. It's a little tough to see, but there's the mineralized shell sitting in there. And we see we have a nice alteration halo around that mineralization. And obviously we start thinking about using that for vectoring towards more ore. So one final animation here just to show you how we tied it all together, if we can hit that one. And we'll just strip away everything. We have iron over titanium sitting in our drill holes, a bunch of structural data there that's going to control our form and turbulence. We're looking down strike of the deposit right now. And then as we rotate around, we'll just look at the results of this alteration modeling first for anything greater than iron over titanium of 300 sitting in there. And as we further rotate this around, we'll bring in the rest of the data. Blue is basically propylitic, green is a chlorite quartz alteration assemblage, and then these are our sericitic alteration assemblages in yellow and orange. Back to granite pit, and we just kind of get back to that same section we were looking at before, bring in our mineralized trend above ground and subsurface, see that similar halo hanging out there as well. So that's about it. So that's how we have been modeling the alteration there, or looking at using this in the future. To conclude, both brittle and ductile deformation are really important there for understanding the deposit itself. So far we've collected about 500 whole rock samples, and from that we've been able to, confidently use, 5,000 aqua regia results to help us model the alteration throughout the deposit. And finally, for me, what I really like about it is it's all dynamic. So you go out and pit map, plug that into your database, it's going to update everything for you in Leapfrog. Same goes with any of your assays that you get back.